Okay, good afternoon, everybody, and welcome to this Gruber Prize lecture. Welcome to those in the audience, and also welcome to those watching us online. It is my honor and great pleasure to introduce the 2022 Gruber Prize winner, Dr. Frank Eisenhauer, for today's lecture. Frank, first of all, welcome to Busan and to the General Assembly. We realize all you have had a little bit more torturous travel to get here, to put it mildly, but we are so happy that you are here and that you are here to give this lecture actually in person. That's fantastic. We heard already a laudatio yesterday, and also in today's IAU newspaper. Please download those and look at those. There's a wonderful story also by Frank that you can read. So what I'll do here for the introduction, as people are still trickling in, is reiterate some of that material, but in slightly different words. So first of all, Frank is actually currently a senior staff member at the Max Planck Institute for Extraterrestrial Physics in Garching, Germany, where he actually spent most of his career. Frank is special. There's no second one like him. As astronomers, we are actually a little bit spoiled, I think, by having access to the most powerful telescopes and getting data delivered in near science-ready form. But we often forget that somebody must have built those telescopes, and especially the increasingly sophisticated instruments on them. Frank excels in the design, the building, and the operation of the most complex astronomical instruments, and then also doing innovative science with them. Most notably, Frank led over the past 15 years the building of Gravity, a superb new instrument coherently combining ESO's 4 8-meter very large telescopes in parallel Chile as an interferometer, and thereby achieving an angular resolution equivalent to that of a 130-meter diameter telescope. Gravity actively corrects for the interfering influence of the Earth's atmosphere, and thereby improving the sensitivity by several orders of magnitude compared to previous experiments, and that has enabled so much new science. Some said that this couldn't be done, technically, but Frank did it. By pushing VLTI to the limit, Frank has led the gravity team to numerous breakthroughs, not only on the galactic center black hole, and thereby testing general relativity in a completely new regime, and that was actually cited in the prize, but also on a wider range of topics. My favorite one actually being direct spectroscopy of giant exoplanets, measuring their spectra with unprecedented detail. Frank, your drive for excellence and never giving up have led deservedly to this success. I think your teams at MPE in Garching and also at ESO Chile are watching online, and we are all extremely proud of you. Let me now give the floor to the Executive Director of the Gruber Foundation, Sarah Riba.
Come forward here. Good afternoon. Because Dr. Eisenhauer couldn't be here for his ceremony yesterday in person, we are happy and honored to present the prize to him officially now, if I don't drop it. Okay. Let's see here. Didn't hurt you. Oh, good Lord. Well, we won't have time for the lecture at this point. All right. I'm going to do something here. You hold this.
We need to make the pin bigger.
There we go.
There we go.
At
The
least I
most
didn't
complex
drop
and
it.
superb instruments.
And shall we? Congratulations.
Thank you very much. And on behalf of the foundation, this is the slightly bigger pin, which you can put on the desk.
Thank you very much.
Thank you, Frank.
Oh. Oh. Oh, please stay.
Okay. Paul, stay for a moment in the video. Here, video. Paul, Sarah, thank you so much. So, to the three of you, dear members of the EU, ladies and gentlemen in the audience, I'm deeply touched and honored to receive this year's Gruber Cosmology Prize. And I thank so much the Gruber Foundation, especially Patricia and Peter Gruber, for this wonderful recognition of our work. And I say our, because this has been the work of many colleagues, postdocs, and students who've built these gravity instruments and symphony instrument, which I will talk about, and have made these observations of the galactic center possible. I dedicate this prize to my colleagues, my late parents, and to my wife and kids who've been with me all along. Let me also use this opportunity to thank for this prize, especially to experimental astronomy. So experimental astronomy is so valuable. It's the basis of the observations and then, in the end, for the understanding of the universe. Building telescopes and instruments like Galileo Galilei back then, and then observe stars and galaxies for the first time is such a special moment, and it is repeatedly is each time you do. So let's work together and carry on this tradition of experimental astronomy to the next generation. So many of you are here in the audience. Thank you very much again for that prize. Thank you.
Congratulations.
So,
Frank,
and
the floor is yours.
the floor is mine. We just made it in time. We made the pin. We made the speech. Now we have to give a lecture. And so this lecture will be about a new era of high angular resolution astronomy. And so you see already some elements which I want to introduce here. And I would like to start this lecture with the element which I said, the team aspects, and many of us coming together. And I would like to start again with the thanks to Patricia and Peter Gruber for the generosity to support and promote science with the prizes and the other programs they set up. Let me also thank Sarah and Stephanie, who brought me here just in time. Let me thank the advisory board. Paul is here. Thank you so much for your support. And let me thank the IAU and the local organizers. Professor Kang with her team here wonderfully put us in a taxi yesterday and brought us just in time for giving this talk. Let me then also thank the teams actually who did the instruments and the experiments and the observations we will talk about today. And so you see three elements here. So on the very lower side, this is our institute in Munich, in Germany. So this is the Max Planck Institute for Extraterrestrial Physics. We are about 400 people who build space experiments and instruments for telescopes. And then there are two teams for the instruments. So the Symphony team on the lower side and the Gravity on the left side. And so these are teams from roughly half a dozen of institutes in Europe. I'll come to some of them below, and together with the European Southern Observatory, who build and then operate this instrument to bring home the stuff. And so let me highlight a few of my colleagues, which I want to point out. My mentor, Reinhard Genzel from the same institute, Stefan Gillissen, who is here with us, from the observatory in Paris, Guy Perron, Thibaut Pavard, Sylvestre Lacour, and Karine Perron from Grenoble. Then we have other institutes in Europe, in Portugal, Paulo Garcia here, the NOVA collaborations in Holland with Paul van der Werf, the Max Planck Institute in Heidelberg, Wolfgang Brandner, the University in Cologne, Christian Straubmeier, and then the observatory. And you see here the former director Tim Desseux today with us, the current director Xavier Bacon, the director of the observatory Andreas Kauber, and my colleagues which have made the observatory work in the instrument, Henri Bonnet, Julien Wallace, Markus Schöller, and Guy Bonnet, who was back then in charge of the instrumentation at ESA when we built Symphony. So we will talk about a new era of high angular resolution astronomy. You see now here two elements. You see the observatory in the end, and you see inset. This is the gravity instrument. So we'll talk about gravity and the very large telescope interferometer, which brought this new era of high angular resolution astronomy. So what is it? In very short, it's the world's largest and sharpest optical infrared telescope. And we do so by bringing together the light from the 4.8-meter telescope in the central laboratory to provide milli-arc-second resolution, micro-arc-second position measurements, and all of that at a sensitivity more than 1,000 times than earlier interferometers. And this led to this revolution in high angular astronomy. So we'll talk about the galactic center, this is the insets here on the top right, but we also talk, if we have time, about the exoplanets, spectroscopy, astrometry, about black holes far away, billion light years away, and not talked about today, but also very, very exciting results on the formation of stars in planetary systems, how the gas is funneled on the surface of the stars, seen on the lower part, or we can resolve images of microlenses and thereby directly measure the mass of the lens, for example. So what I want to bring to you now is a 30-year journey towards the galactic center. So this is an image of the galactic center as you see it at optical wavelengths like your eye. And you actually don't see towards the galactic center, it's dark, because there's a lot of dust along the line of sight, which obscures the light. And you can only see in X-rays or radio or in the infrared, and this is what is coming up now. You see to the very center, and in the infrared, you see a star cluster in the center, millions of stars orbiting around the very center of our galaxy. And so this was the wonderful period of the 90s. This is when I started my PhD. It was a wonderful time. You were traveling around several times a year to different observatories, bringing your small instruments. So this is why I call it the epoch of experimental astronomies. The instruments were of a size that you could still carry them around with an airplane. It was the time when infrared detectors became available. We started to learn how to control the atmosphere, and we learned how to do imaging spectroscopy. I'll touch on that with Symphony. And so in this period, in the 90s, late 90s, we've seen for the first time the stars move in the center of the galaxy. So this from Eckert and Genzel in 92, 93, the left panels. Our colleagues at UC in Los Angeles around Andrea Ghez could measure the acceleration of the stars, and with integral field spectroscopy from our institute, we could measure the spectra of the stars. So wonderful time with very small, comparatively small instruments by these days standards traveling around. So how could we bring this tradition of experimental astronomies to the time of large science facilities which were coming up at the time? So what you see in the background is the Parallel Observatory from the European Southern Observatory. 4 8-meter telescopes operated like a factory in a way. So how could we bring together experimental astronomy and this large science facility? And so we put a proposal end of the 90s for the Symphony instrument, a fast-track instrument which we then could rapidly actually build and bring to the telescope. And in 2003, then we could make it work. So what is Symphony? So Symphony is a combination of 2 techniques which were arising at the time. So one, adaptive optics on the side. I'll touch on that in a second. And the key to Symphony is a technique which is called imaging spectroscopy. So when you make an image, you would also like to have for every pixel of the image a spectra, the physical characteristics of the object. So how do you do that? There are different techniques, and these are illustrated on the left side. You can either put on every pixel of your image a fiber and then make the spectrum of the fiber separately. You can put a lenslet, or the technique which was pioneered in our institute is what we call image slicing. And so image slicing works like that. You have 2 sets of mirrors, a tiny one on the right side, 32 lines of mirrors de facto, where you slice line by line the focal plane of the telescope. You send the light in different direction, catch them with a second set of mirror, which you see in the background, and then send towards a spectrograph, a long slit spectrograph, and do the spectra for every pixel. And so now we could go to the next phase of this galactic center experiment. No, please let me first introduce adaptive optics. So adaptive optics is now to overcome the problem that the Earth atmosphere is turbulent. From the heat you have turbulence. Turbulence blurs the image. And the way we correct it is we measure this blurred image, which reflects in a curved wavefront, 1,000 times per second. We send control signals to a mirror with many actuators. And in the end, you flatten the wavefront. This is our physical way of saying it. And you recover the full diffraction limit of a telescope despite the atmosphere in between. So SYNFONY is the combination of the two. The first, adaptive optics assisted integral field unit at a 10-meter telescope, and then we could continue our journey. So now we go from the seeing limited observations to adaptive optics limited observations. So what you now then see, if you zoom in farther, and now we are reaching levels of a light month around the very center, more and more stars appear, and you do not only see the stars move, but you see especially one of them, this is the star S2, to move in an orbit. In an orbit, an ellipse, like a planet moves around the sun. And so you can do the same experiment, like you measure the mass of the sun from the period of the planets in the distance. You can do the same with high school physics to measure the mass of the dark object in the center. And so this was the big period around 2003 to 2005, when it was really becoming obvious that there's a very massive 4 million times the mass of the sun dark object where the stars move around. We have not only measured the orbits, but now with this technique of integral field spectroscopy, you could measure the spectra and thereby the line of sight velocity, so whether the object is approaching or receding you. So it gives the third dimension. You can get the full orbits, this is what's seen in the middle, in 3D, and you can also look at emission lines coming from gas and see how gas is streaming into the center of our galaxy. So this was 2005. The state back then in observation theory was like that. You see on the top left, every once in a while, once per night, the black hole gets a little bit brighter. It has a periodic brightening and dimming, and this is indicating, and this is in the theory on the lower side, if you interpret this period half an hour, this could be a hot spot which is moving around the black hole very close to the event horizon. The other thing which we've done, or had at the time, we had the stellar orbits as I introduced, and then you can do a prediction. If you go farther in, and if you can measure more precisely, you should see actually the relativistic effects in the orbits of the stars, not Kepler motion anymore, but deviations as predicted from general relativity. So this is what we had of the observations in the theory side in 2005. Then at the same time, it was the period when the community started to put big telescopes together as an interferometer, as a single big telescope. And this was also when technology was arising from telecommunication with single mode optics. This de facto are single mode fibers, as you know, from telecommunication, but now carried to the wavelengths we use in astronomy. So this was the state. And so now what could we do? Actually, if we bring the two together, we should be, and this was the prediction in 2005, we should be able to see this motion of matter around the black hole. That's what you see on the lower left. And we should see stars farther in and be so precise to measure the effects of general relativity on the orbits. And so how do we do that? This is this gravity experiment which Emil already so nicely introduced. We have to bring in the 4 telescopes. De facto, we do a double slit experiment and observe a fringe interference. But to interfere the light from 2 telescopes, you have to do that at a fraction of the wavelength, so for us to a few hundred nanometers. So in here we follow the light through the observatory that you get a feeling of what all has to be done. So the first thing which you have seen is we bring the light down into the basement of the telescope. This is what you see here, and this is where we are having our adaptive optics. So this technique which I explained you before, which measures 1,000 times per second the shape of the wavefront, the image, and corrects 1,000 times per second the turbulence or the effect of the turbulence. In our case of gravity, which was particularly built to observe the galactic center, we do not see stars at visible wavelengths around, so a key was the development which we have done together with ESO and Selex, a company in England, to develop now and have available for the first time infrared detectors which are de facto noiseless. And so they were the key for our instrument to get the sensitivity, both for the adaptive optics, but then also for the interferometry. Now, so we've prepared the single telescope. Now we have to bring the light from the telescopes together, and this is now what you see in this animation. So we bring the light through tunnels, this is what we call it delay lines, to compensate the path lengths, and we bring it together in the central laboratory. This is called the Very Large Telescope Interferometry Laboratory, and we build an instrument, the gravity instrument. It's a cryogenic instrument because we work at infrared wavelengths. We cool it to not see the thermal radiation. And this is what you see here. So we have a vessel which is cooled and hosts all of the electronics and optics. So we go now again first with a single telescope and see what we have to do. So we not only have to correct the sharpness of the image, but we also have to correct everything which has happened on this 200 meters between the telescope and the instruments. So we have mirrors which actively steer the beam, and we send laser beacons up and down from the telescope to the instrument and from the instrument up to the telescope. We monitor that, we have a metrology, and we measure that in some of the elements you see in this animation, where in our language we observe the pupil, we observe the field, and we control all of that on diagnostics like that, which we have in the instrument ourselves. So now the light is prepared from the 4 telescopes to arrive in the same place in the observatory. We have not done yet interferogram, a double slit experiment. And this is what we do in single mode fibers. So we couple the light from the object we want to observe into single mode fibers. You can stretch them. This is what you see here on a coil. You can actually also physically twist the fiber, thereby adjusting the polarization, so the direction of the electric field, and then bring them together. And then the light arrives from the telescopes, which are 100 meters apart, at the same time 100 meter in equivalent, and you can actually start to interfere them. And the interference then is then done like a Michelson experiment, but instead of using a beam splitter and mirrors, we implemented in a little chip like that, which is called integrated optics, the equivalent of an electronics integrated chip, where you have the functions imprinted in the light path of this chip, and in the end you create an interferogram. This means the superposition of the light from 2 telescopes, what we call fringes, which you see here in the vertical direction. And so the measurement, the quantity which we measure is the strength of the interference as a function of wavelength for all combinations of the telescopes. So we have 4 telescopes, 6 combinations, 6 different colors, and then you measure that at different times of the night, and you can reconstruct the image. The mathematical relation is simple. It's the Fourier transform. Then you clean it, and then you end up with an image like that. And so what you see here are 2 images. It's a true observation. One is the star, the brighter object, which is falling around the black hole, and the black hole itself. So this now brought us to the last step of our journey. So here you still see the adaptive optics of a single image. And now with interferometry, with gravity, we get yet 20 times sharper images. We are so sensitive that we see the black hole all the time. The star is falling around. We can see it move day by day. And in 2018, it has its closest approach, was moving by 2.5% the speed of light around the black hole. And so this was then also the time when the case was really made that this dark object in the center of the galaxy is a black hole, and for which the Rainer Genzel, Andrea Ghez, and for the theory side, Roger Penrose were awarded with the Nobel Prize in 2020. So this is where we stand. State of the art now with gravities. We can so precisely measure the motion of the star, and with SYNFONY measure the line of sight velocity. The ratio between the two de facto gives you the distance, and we can measure the mass and the distance at the same time, now to sub% accuracy. We can look on finer deviations from Keplerian orbits to see the effects of general relativity. And there are 2 effects which I want to introduce. One is, which you see here, is when you get with your clock closer to a black hole, time goes slower. And the equivalent is the atoms oscillate slower, So the light is a little redder than it should be. And so we can observe it as a gravitational redshift on top of the Doppler effect. And this is what you see here in this curve. You see over time the deviation between the line of sight velocity between a classical Kepler orbit and what you would have if general relativity actually makes your clock go slower. And this is what you see here, very clearly detected. By now, we are more than a 25 sigma to have this effect detected. The other one is that not only time goes slower, but space is curved. And this leads to a situation that the ellipses, which you know from a Kepler orbit, do not close anymore, but that they precess. This is called a Schwarzschild precession. The effect is small, therefore you need the high precision of the gravity interferometer. And now, 2 years ago, we've been able to also measure this effect, which you see on the lower left side. So you see the orbit 16 years ago in the red, in the new measurements, now with the gravity interferometer 2 years ago. And so we can now also detect the Schwarzschild precession, this rotation of the orbit, or the 8 sigma level. Now, what else can you do with this experiment? So we have two objects in our images. We have the black hole in the center and the star. The star is moving over days and weeks around. Within 1 hour, also something happens. Actually, if you measure the separation of the two, you see even within an hour a change of separation. This happens when the black hole shines up, when matter is accreting. And this is the measurement we got in 2018. Now we are on a very, very tiny scale. It's already the scale of the event horizon, 10 times the event horizon, what you see here. So what we see over 45 minutes, you see that the black hole, the emission from the black hole, is moving around the black hole at 30% the speed of light in 45 minutes. There are some other characteristics of these flares, not only orbital motion, but you can also see the Doppler boosting. When the object approaches you, it gets brighter. We can observe the polarization, and all of that we could interpret back then to give a physical interpretation of what we see, a hot spot orbiting pretty face on around the black hole. As I said, it's 30% the speed of light. And the magnetic field and the energetics there dominated by magnetic fields which are probably vertical in this picture, aligned with the spin of the black hole. Now, this year, the Event Horizon Telescope could also release the image of the very same object, the black hole in the center. This is the overlay of these two. In the background, you see the image of the black hole seen by the Event Horizon Telescope. So this is at millimeter wavelength. You see the diffuse emission around the black hole, or more accurately, you see where the emission appears brightest, and this is the photon ring, and this is why it looks like a ring with a shadow in the middle. And you see in the colored points around, this is the motion of the hot spot which we have observed in 2018. So by now, you can really put the two things together. You can derive either from the orbital motion, which is shown on the left, or from the size of this ring from the image. This is on the right. You can derive a mass at the separation. And when you bring this together in this plot, this is a summary now of this journey which I showed you of 30 years, is the enclosed mass as a function of separation. So we start out at about a light month, light year, where the stars dominate the potential. So you have to look on the top curve. I don't have a pointer, unfortunately. And then you go in, and then you see that the curve flattens. The enclosed mass does not change anymore, so it must be dominated by a single object, and it is dominated by a single object all the way when you go to the left to the measurements I just presented at a few event horizon scales, by the flares we've measured with gravity, and by the size of the shadow measured with the Event Horizon Telescope. So we have no doubt, I would say, that what we see is consistent and well described with what we call a Kerr black hole. So Kerr black hole, this metric is a description of a rotating black hole. And so now you can go to the next level. You can say, is it really a black hole? Does general relativity hold? And you can parameterize in the most not simple, but in In the lowest order, you can parameterize the size of the event horizon and with a deviation factor epsilon, and you can say, are our measurements consistent with this solution or epsilon of being 0? And so right now we are left there. Everything which we have measured, be it in the X-rays, with the iron lines, or with gravitational waves, or now with these experiments in the galactic center from gravity and the EHT ring, we can say within order 1, general relativity holds. We have not seen deviations. So can we go beyond that? Can we measure epsilon better to actually see potential deviations from general relativity? And yes, we can. And the key to that is another parameter in these numbers is this A. This is the amount of rotation of the black hole, the spin of the black hole. And with our instruments, gravity, and then what I will show later, with the big telescopes to come, we should actually reach that. So we should be able to measure the spin. You might even be able to measure the quadrupole moment, so another description of the gravitational field around the black hole in the years to come. So how to do that, and I'll illustrate that with another animation. This is to measure the spinning, the rotation of the space-time around the black hole. So we are not only curved, but we rotate. Well, we don't have a rocket, but we have other matter rotating around. So how can you measure the amount of spinning of a black hole? And the simplest one is how close you can get with your rocket or with your orbiting matter. The closer you come, the faster it goes, the higher is the redshift, and the smaller it is. So these are the classical measurements, but you see all of these measurements, size, period, or redshift, they also scale with the mass of the black hole. Is there a cleaner way of that, so that the effects are disentangled between mass and spin? And yes, it is if you go out of the plane of this rotation of the space-time. So if you find a star which is rotating not in the plane of the rotating space-time, but say on a polar orbit, it will deviate. This is called the Lense-Searing precession. It's very small, so we need to measure ever better. And it's the stronger, the closer you get to the black hole. So we need to find stars which are farther in. And so this is what we are doing. So where are we right now, 3 years after this one star has passed the black hole? The star has moved out of the field. Now we can look even deeper. The star was so bright that it was blending. So now these are observations from last year, from a few months. So now what we see is we see 5 objects in that field, which I've showed you before. 4 stars there. One of them actually gets closer than the star I showed you before. One of them is on a shorter period than the star. And one, this is what is showing here, is much, much fainter, 100 times fainter than this famous star with the 60-year orbit. So far, we had not yet found a golden star to measure the spin, but you see, this is where we are going. And so we are starting to mosaic around the center of the galaxy with interferometry now, like in radio, de facto all carrying to optical infrared astronomy. Something now I have to emphasize you cannot do with a single telescope. So on the left side, this would be the equivalent when you have adaptive optics on a single telescope, and on the right side, the true observations with interferometry. So we repeatedly observe the stars. Now we can do the same probing of the gravitational potential, not only for a single star, but for a handful of stars, which allows us to measure the amount of extended mass, for example, stellar black hole remnants or neutron stars there. And so what we found is, de facto, there's very little. We have less than a 3,000 solar mass of these additional dark objects within the orbit of the star S2. Now, what we cannot do with interferometry, but what you can do with single telescopes is you do not have the resolution, but what you will have, and this is what we are building towards, in Europe, the extremely large telescope, in the US, the equivalent 30-meter telescopes, is you have a large collecting area. Large collecting area will mean even if you cannot resolve the individual stars in your spectra, you will also see the signatures of the faintest star in the spectra. And if you go to fainter stars, They are colder. If they are colder, you see more and more molecular and metal lines in the spectra. This is indicating on the lower left. So you have a comb of spectral lines which then allow you to even more precisely, several orders of magnitudes again, the velocity of the stars in there. And then you can think of what is currently, I would best describe as pulsar science. You can very well measure deviations again from the orbits, from Newtonian or first order general relativistic effects, and go to higher effects to detect them. And our prediction is that we will be able to go all the way to measure the quadrupole moment and thereby now put limits on deviation from the Snow-Hair theory, which links the spin and the quadrupole moment together. So a very bright future ahead in galactic center research. Now I have a few more minutes to also touch on the other revolutions in astronomy which we have seen. And I would like to start with the exoplanet spectroscopy here. So as an introduction here, you see on the top right a figure which shows you planets, the characteristic of planets in two parameters, how far they are from the star, from the left to the right. So points to the right are farther from the star, and then the brightness or the contrast ratio between the planet and the star on the vertical axis. And we have three groups of planets determined, so to say, by the technique you are using to observe them. So you see mostly the stars which are close in this technique which is called transit spectroscopy. This is, for example, where James Webb now will bring a real breakthrough in the spectroscopy of those stars, where the planet move in front of the star and you see the dimming, or you can look on the reflex motion of the star. When the planet goes around the star, it moves the star. These are called radial velocity planets. Or if the planets are far out, you can directly image them. And I show you two examples here. So the star is blended out with a coronagraph. You only see the star on the top left is a very famous system. Beta Pig B is the planet, which you see here in the adaptive optics image. But the problem with that is that you actually cannot go close enough in, and that you cannot get high enough contrast to see fainter objects. And so we are limited in this diagram on the right to this green area. Now with interferometry, we can do both. We can go into this black part where the coronagraph blocks the light of the star, and we have the resolution, for example, to distinguish whether these dots, which you see here on the lower side, are truly a planet or concentration of gas. And so what we've done, and this started in around 2020, when we for the first time were going into this interferometry of exoplanets. What you see here now is the gravity observations of the exoplanet Beta Pig B, which you see on the top left. Now with the interferometer, we can very well distinguish whether the photons come from the planet or from the star. We can separate them in their what we call fringe spacing. And so we can then derive a very high signal-to-noise ratio spectrum of the atmosphere of these very massive planets. You see molecular lines here, for example, carbon oxide, and then you can go to Wiener or others and let them analyze and see what is in the spectrum, and you will see that the carbon over oxygen ratio is actually too low to what you would expect if the planet has directly formed from the gas. So even these gaseous planets, much more massive than Jupiter, must have had a substantial accretion from planetesimals or icy things which have less of a carbon in there. This is what is illustrated on the lower side. But now you can do more. Actually, you can go into this dark region and you can see whether there are other planets. And so we knew that there's an other planet in the system from the reflex motion of the star. And now with gravity, we for the first time could detect one of these radial velocity planets, so this Beta Pig C in the very center of that. We can actually measure the positions, the orbits of the planets so well that we see how the planets are shaking the star. So what this means is now you can actually measure how heavy the planet is directly. And so for two of the systems, now we have dynamical mass measurements of the planets. For for this better pixie, and you see we are already at very high accuracy with these dynamic measurements of the masses of the planets in the systems. And so the last thing which we are now approaching, and is towards the future, is there will be a big set of new exoplanets coming up from the Gaia mission. So Gaia is a satellite mission which precisely measures the position of stars over many years. And when you see the stars wobble around, you have indication where the planet should be. And this is one of the predictions from a candidate from radial velocities and constraints from Gaia. It's predictions where the planet should be. And so we started to point at different fields of this prediction. And finally, actually outside the prediction, we now can report for the first time, I would call it a direct detection of radial velocity Gaia astrometry exoplanet to be published very soon. And so this is the revolution we see on the exoplanets. But we also go far out, and so now I go to the top panels of this overview figure. So we will talk about black holes. Black holes, 1 billion light years ago away. And so they are called active galactic nuclei. So every big galaxy hosts a black hole in the center, between a few million and 1 billion times the mass of our sun. And then depending on the current situation, they appear differently. There are a few main characteristics. So there's the black hole in the very center, which shines up when matter flows in. This is called a quasar, so bright that it outshines the full galaxy. Or if there's less of accretion, just some, you would see the black hole, but then depending on the viewing angle and depending on how much dust you have around the black hole, you see it brighter or less. And last but not least, very close to the black hole, you have ionizing radiation. So the gas around the black hole will be ionized, and you can see it in the spectrum as an emission line, which is very broad from the Doppler rotation. And so now with interferometry, we can go on these different scales. So now in the last 2 years, the VLTI has been able now for the first time truly image this hot dust around the black holes. You see on the lower left side, the image at somewhat longer wavelengths, 5 to 10 microns from other interferometric instruments, Matisse. And on the right side, the inset to one region at shorter wavelengths, 2 microns from gravity, where we are a bit sharper. There you can see the fine structure of this dust around the black hole. We can also go to the very center. Now we look on scales which you cannot see in here, so there's emission lines coming. This is this broad line region. And now with interferometry, what you can do is you can at the same time measure the velocity of the gas, and you can measure the position of the gas. And this is what is shown here on the lower side, or the very famous quasars, the first quasar discovered, 3C273. You see in different color a different velocity. The change is several thousand kilometers per second. And then where on the plot? This is the position on the sky. And so you see that the gas is moving away on the lower side. It is coming towards you on the top right. What you see here is a rotation curve of the gas. So you know the separation, you know the velocity. You can now directly measure the mass of the black holes. So for the first time now we've been able to spatially resolve this broad line region. So we have a way to directly measure the mass of black holes. This one is roughly a billion light years away. But this is not where most of these objects were forming. Most of the objects, the black holes, in galaxies, everything de facto, was forming about 10 billion years ago. This is what we call cosmic noon. Can we directly measure the mass of the black holes there? So far, there's no direct measurement possible, only indirectly. But now with gravity, we can do, and what you see in the central panel on the right is the size of the object as a function of, now in different color, what is shown here, the distance to the object. And so what you see actually, and this is surprising, the more distant the object is, the objects appear larger than in the local universe. So the objects in the brown curve, they are at 10 billion years ago. The other one, the local universe, are the blue symbols. And so why is that? This is the reason, because if you look at a large distance, you also have this cosmological redshift, which means that light is redshifted, so the light which is originally coming in the optical is moving to the band where we observe with gravity. For these objects, it means if you look now at optical wavelengths at high redshift, you do not see the hot dust anymore. You only see these emission lines which we want to trace, and this is why the objects actually get fainter but larger. And so how can we get there? And we are very proud to report here now our first tentative detection of a rotation of a broadline region of a quasar at a redshift of 2.5, so 10 billion years ago. You see again the same signature position. Now the vertical axis is the position as a function of the wavelength, the velocity of the gas. So how do we do that? And the trick now is the galaxy itself, the quasar, is too faint to run all our control loops of the interferometer. But instead, and this is what you see on the left side, we look for objects which are nearby a bright star, the more reddish object here, where you run all of your control loops of your interferometer, and then you can make exposures of minutes to hours on the faint object. This is what the more bluish one with the blue cross, this is the quasar, and get to these measurements. And so this is the first step of a new project which we've started together with the European Southern Observatory and again a handful of institutes in Europe, is what we call the Gravity Plus upgrade of gravity in the VLTI. And this has several aspects which I would like to introduce in the end here. So there's this one mode where we actually run our control loops on a nearby star. This allows us to come to 100 times larger sky coverage to actually go to this kind of observations which I showed to you. So we'll open up the extragalactic world with this new mode. And then we work on to getting ever fainter. And here we are currently mostly limited by the ability to control the wavefront with the adaptive optics. So we are upgrading all our telescopes with laser guide stars. We are putting new adaptive optics to all of the telescopes. And we are working on the sensitivity of the instruments to achieve in the end in a factor 10 to 100 times more sensitive observations. And with that, I would like to thank you. We have a very bright future ahead with interferometry, and I would like to thank you again and like you to join. Thank you very much.
Thank you so much, Frank, for this absolutely wonderful and beautiful presented talk and showing that when you drive instrumentation to the limit, you find new things and fascinating new things. We started this talking about torturous journeys, but when I saw your movie again, the beautiful one where the light comes into the telescope, but it's also a pretty torturous journey for the photon to get finally into your instrument, but you controlled it all.
Torture it. No.
Good.
We notch it.
We notch it. Good. There's time for some few questions. So please line up to the microphone. Please, there must be some questions here. So there are some microphones there that you can line up and ask a question. And yeah, I see there. Go ahead.
Hello, Keith Bannister. Excellent talk, thank you very much. My question was just about why you choose for a Redshift 2 galaxy to measure the broadline region. It seems like making your life difficult for no reason, for an amateur.
Question. So the reason is that this is the H alpha line. So you are in the rest frame optical. So the thermal emission from this hot dust you don't see anymore, and the H alpha line is a very strong line. In the end, our relative motion, what we measure is the motion of the centroid across the spectral line. So what enters is directly the ratio between the line strength and the continuum. And so when we go to redshift 2.5, we go there because our instrument only works at 2 microns, so you can calculate when H alpha goes in our observing window, and this is the redshift 2.5, which is so Well, I would say by chance so well matched to the peak of the evolution of the universe.
Maybe if I can follow up on that with a question, because you have, for good reasons, chosen to work on the K-band. What are the prospects for extending the wavelength range, which might be beneficial for some projects to, say, L-band or shorter to H-bands?
Well, both directions we go.
Yeah.
The prospects towards longer wavelength is already there. This Matisse instrument, so this then picks up at L-band, so from 5 microns, then all the way to 15 microns or something like that. Here the limitation is that on Earth there's a thermal background from the observatory, so it will be very difficult to here realize another factor 100 or so of sensitivity gains because we are already in the thermal background limit. Mm-hmm. Yeah. Now on the short wavelengths, it's a very obvious way also to go. It's technically more challenging because the wavelength is smaller, but not only the wavelength is smaller, all the perturbations are faster. And this fast is our main limitations because all of the control loops have to go faster, and therefore you need more photons to run them. And so this technique of fringe stabilization for the moment works in K-band very well. In H-band, so H-band is 1.6 microns, just, I would say. Now to go to 1 micron or to optical light is a way I would say we are not there yet. And the limitations is actually, well, we walk observatory like we've seen here, these big telescopes, it's like a factory. Things breathe and vibrate, there's cooling, there's fans. And so this is what we are doing with Gravity Plus. We are actually trying to improve on all of the fronts, the perturbations, and then we can also hopefully soon go to shorter wavelengths.
Yeah, okay.
And then we could get closer in and then maybe come to reflected light of exoplanets, for example. Yeah. For the moment, we observe the thermal emission of the planets, so we look on very hot planets. They do not look like the planets in our solar system, but they are 1000 Kelvin still. And so they are still cooling these planets, and this is where we want to go ultimately.
Yeah. Well, step by step, and who knows, in 10 years or 20 years' time.
We'll make it in 20 years.
Yeah, okay. Good. Any final question? Please, there is still time for 1 or 2 more questions. Feel free to go ahead. If not, there's a question. Yeah, maybe you should shout, or let's go up, up the stairs. It's good. We keep our participants healthy.
We should do that.
So Frank, you have very wonderful instruments. So how do you compare your gravity to JWST? So what do you expect if JWST is the galactic center or future instrumentation for with space telescope?
Well, let me ask in 2 ways. I would say for the galactic center, James WST is too small to compete with our angular resolution. So our 100-meter telescope will outperform here by far for a long time to go. Now, a different question is whether James Webb is such. Of course, it's a different category, I would say, in price, in the way it's done. We talk about a 10 billions versus a 20 millions experiment. Well, we are doing different things. Also, the pace of innovation is a very different one. This is why I was stressing so much in the beginning and in my thanks to the Gruber Award, this element of experimental astronomy. We see it, this experimental part is a bit falling behind against the industrial style of building instruments. So James WST is a project we could not handle as scientists. And it also comes with disadvantages. I think it comes with these disadvantages that we lose the education to the young people to build the next generation of these instruments. It comes with being very conservative. Well, James Webb is not conservative with mirrors, I admit that, but overall space is quite conservative. So I would say when we started Gravity, there was almost a consensus, maybe with exception of Tim, who was the director back then at ESO, that gravity will never work because it's too innovative or too challenging. And these are only things you can do in this experimental mode at the observatories here. And I really want to make a case to keep this experimental mode as one part of this culture which we have in astronomy.
Good, that's a perfect way to end this Gruber lecture. And let's give Frank one more big round of applause.
Thank you very much.
Thank you so much. Thank you so much. Good. And this concludes this lecture. So I think the next set of lectures are starting at 1:30. So see you tomorrow here for the next lecture. The Kavli Prize lecture will actually be here at the same time, 12:15.
Thank you very much for being with us.